Good afternoon, students. Today we are going to continue the last class, which is nothing but data acquisition system. So there are two types of data acquisition systems. One is a unlocked data acquisition system. Second one is a digital data acquisition system. Unlocked data acquisition system and the digital data acquisition system. Depending on the way of recording the information, whether the information is stored in unlocked form or the digital form, as we know that two types of data acquisition systems are there. I'm not going to elaborate that explanation, but what I've done is in the last class means I reviewed the last class video. I thought I missed out some points regarding when we are connecting our transducer to the data acquisition system. Okay. So here we are connecting the transducer to the data acquisition system. That is nothing but this particular recording section available in the remote area. Remote area is nothing but where we are having the actual control block of the industry, where we are measuring the where we are observing the information, displaying the information related to a particular variable which is sensed in the industry, somewhere in the industry. Okay, means we are sensing some physical parameters, as we know. Okay, so when we are using this is the communication path to communicate our transducer measuring element with the instrumentation amplifier. Between these two we are having the communication path. So here I told that there is the involvement of the noisy signals into the communication path when we are placing this communication path near to the high voltage wires. So in the industry, the instruments are going to be working with the high voltages. Okay, so there is a chance of the high voltage means when we are taking the low electronic signals near to the high voltage signal, there is a chance of introducing the noises into the communication lines which are working with the low signal, low electronic signals. Okay, so that noise, how it is going to be introduced into the our system is it is going to be in terms of what radiation. It is just because of the radiation, or it is just because of the ground loops, the current leakage which is passing to the ground, which we have seen so in the last class. So because of that, the noise signal is going to be introduced into the actual communication path. So here in this diagram I missed out one point. I thought that is the point which I would like to mention over here. So here this is the heavy line wire, high voltage wire. In near to this we placed our our communication path is taken up. Means we are taking the communication line under this particular wire. At that time, what will happen? If you see this one, this line as well as this line looks like a parallel line, as well as this line and this line looks like a parallel line. So as they are looking like a parallel line, they are going to act as a capacitors, parallel plate capacitor. Don't think that these capacitors are externally connected to the way other wires with our actual communication path. It is not like that. The main intention of this diagram is describing that these two lines are forming one kind of parallel plate capacitor, and these two lines are forming the other kind of parallel plate capacitor. So when we are having the capacitor, so obviously the information is going to be induced into the wires. The information is going to be induced into the wires as they are acting as a parallel plates. To what we are going to do means here, when the noise is going to be introduced in this particular system, as we know that this information is given as an input to the instrumentation amplifier. So the instrumentation amplifier, what it will do, it is having the common voltage, common mode rejection ratio, common mode rejection ratio. So because of the common mode rejection ratio, what will happen? These noises are the noise introduced because of the heavy lines into the actual communication path. Actual communication path, they are going to be introduced equally into this one as well as into this one, They are equally introduced into these two parallel lines, and they are going to be rejected by the instrumentation amplifier, which is used right over here, because the instrumentation amplifier is having the common mode rejection ratio. Because of that, the noise is introduced into this communication path is going to be nullified. So other cases, I'm not interested to allow my communication lines to form the parallel plate capacitor like scenario with respect to the heavy voltage carrying lines. What I'm going to do is, as we have seen, I'm going to use the jocket, which is acting as a shield. So this jocket is going to be protect our communication path. So if you see this one, again, this particular jocket is acting as a parallel plate with the heavy line wire, but this one, there is a means, but this wire is forming the parallel plate with this jocket now. Even though we are having the jocket, there is a chance of involvement of the noisy signal, which is what induced over here, that may be propagated through the jocket and entered into this wire. Okay, that may be propagated through this jocket and enter into this one. Okay, there is a chance. So because of that, what we are going to do is we are using the jocket now. So this jocket is connected to the ground. Okay, now. So whatever the noisy signals which are trying to induce into our communication path, those signals are going to be bypassed to the ground via the what is that device device box. We are having the device now. This particular device out box, the body of the device is going to be connected to the ground, and this wire is going to be connected to the this particular body, the device body. So from there, it is the signal which is coming from here, it is going to be driven to the ground. So we are simply bypassing the noisy signals involvement, which are going to be involved when we are placing the communication, when we are placing our measuring system, data acquisition system under the heavy line wires. To avoid that one, we are using the shield. So this is what I would like to recollect in the last class. So I thought I missed out those points during the last class. So because of that, I am coming back to this slide. So don't think that these are the externally connected capacitors. Actually, it is an indication that this line as well as this line both are acting as a parallel plate elements. So they are forming the parallel plate capacitor. So that is the scenario, but it is not nothing to do with this. Means we are not using any external capacitors to communicate this wire with this one. Okay, now don't think like that. But they are forming the capacitors like scenario. Because of that, the what noisy signal is going to be introduced into our communication path. That's it. So don't think that they are the externally connected capacitors to some other device. Okay. So the next case is, now I would like to communicate. I would like to send my information. Let us suppose my measuring area and the remote area. Remote area is nothing but the base station where the workers are going to be work, and they are going to be observe the present measuring variables. That area we used to call it as a remote area or the base station in the industrial case. So here, in order to drive that information, from the measuring area to the remote area in the industry, what I'm going to do is I'm going to use the communication path lines. With the help of the communication path lines, I'm going to transfer the information from the transducer to the measuring device. Sorry, the transducer to the displaying device. Okay. So here what I'm going to do is I'm using the transducer. As usual, instrumentation amplifier is amplifying the transducer signal, and here I would like to drive the information in terms of the frequency, not in terms of the voltage. Because we have a scenarios that when we are trying to send the information in terms of the voltage, as it is passing through the cable, because of the certain characteristics of the cable path, the path which we are using, the voltage intensity may be reduced. At the destination, we may not recollect the same information. So because of that, instead of sending the information in terms of the voltage, I would like to send the information in terms of the frequency. So that's why I'm going to use the voltage to frequency converter. The same, I'm assuming that sensory information is available in the voltage format, and that information is going to be converted into the frequency format with the help of the voltage to frequency converter. I'm not giving the elaborated explanation related to the voltage to frequency converter because we covered this topic in the third semester. So please recollect that information when you are going through this particular one. So nothing to do this one with this setup. Only the thing is how the information is going to be transferred. So the information is transferred in terms of the frequency format. At the destination, I'm using the frequency to voltage converter to recollect the information in terms of to recollect the information and represent the information in terms of the voltage. Finally, the information is going to be displayed on the analog meter. So this is the setup to send the information from the measuring area to the base station or the remote station. Okay. So this is the communication path now. Here we are sending the information in terms of the electrical signals. Here we are sending the information in terms of the electrical signal. And also I'm displaying the information on the analog meter. Let us suppose I would like to display the information in terms of the digital variables. Okay. I would like to display the information in terms of the digital, not in terms of the analog. Then what I'm going to do is I'm going to use the same setup, but instead of using the analog meter, I'm going to use the frequency counter, which is going to be display information in the digital format. So here we are using the transducer, again the instrumentation amplifier to the voltage to frequency converter, which is converting the information in terms of the frequency and sending the information in terms of the frequency to the destination. In the destination, we are using the frequency counter, which is going to be displays the information in terms of the digital, not in terms of the analog. And whatever the communication path lines which we have seen till now, this communication path line and this communication path line, we are sending the information in terms of the electrical signals. That may be the voltage, or that may be the frequency, or sometimes it may be the current also, depending on the how we are sending the information. But the current format, which we are not showing right over here, we may have the different means the information is going to be transferred in terms of the electrical signal. So when we are transferring the electrical signal, there is a chance of inducing the external, means the external parameters. Heavy line wires are going to be affecting the actual information which is passing through the communication path. To avoid this kind of problem, means involvement of the noisy signal and affecting the actual signal which is passing through the communication path, what I'm going to do is I'm not going to use a normal twisted pair line connection or a normal wire connection. Instead of using the normal line connection, I'm going to use the fiber optic communication. Means I'm using the optical fiber as a communication path. So what is the advantage of the optical fiber compared to the other things? In other cases, we are supposed to send the information in terms of the analog or the voltage. In other cases, we are supposed to send the information in terms of the analog or voltage. But in this case, in terms of the voltage or the currents or the frequency format, means which is in the electrical signal format. But in this case, using the optical fiber communication, we can send the information in terms of the in the light format. Means in order to send the information through the optical fiber, whatever the information which we are trying to send, that information should be given as an input to the transmitter. Inside the transmitter, we are using the laser or the LED to drive the information in terms of the light, not in terms of the electrical signal. So here the voltage to frequency converter is there now. This voltage to frequency converter, what it is doing is voltage to frequency converter, what it is doing is it is converting the information into the pulse format. This pulse format is going to be turn on, turn off the laser. The laser is acting as a transmitter. So here, as the laser or the LED acting as a transmitter, then the information is going to be transferred through the glass fiber or the optical fiber in terms of the light. And at the destination, I'm going to use the fiber optic receiver. Means the receiver is also the laser or the the receiver is also with the light detecting element. So which is going to be detects the light coming through the fiber and converts that information into the pulse format. Pulse format is again converted back into the voltage form using the frequency to voltage converter. Finally, we are having the analog data output. Here we are sending the analog data input, and here we are receiving the analog data as an output. Okay, now, so what is the advantage of this communication path? In the normal case, we are sending the information in the electrical signal format. There is a chance of introducing the noises because of the high voltage signals which are there in the industry. To overcome that one, instead of using the normal wires, we are going to use the optical fiber. In the optical fiber, we are sending the information in terms of the light, not in terms of the electrical signal. Of course, the electrical field should be there, the power supply should be sent along with the fiber, but the information is not going to be sent along in terms of the electrical signal. The information is going to be transferred in terms of the light. Okay, so that is the advantage of using this. So this is the conclusion of our data acquisition systems. Okay, now data acquisition system is nothing but which measures and stores the information for future use, records the information for future use, depending on the format, whether the information is stored in the analog format or in the digital format. Depending on that, then there are two types of data acquisition systems. One is a digital data acquisition system, another one is the analog data acquisition systems. Okay, this is the conclusion of our analog or the digital data acquisition systems. Okay, so next topic in our case is we are supposed to study about our there is a multiplexers, continuation to the syllabus. So second half of the syllabus is a multiplexer, right? As per your knowledge, what is a multiplexer? All of you know this one, right? We have seen this one also, and we have done some practicals in the electronics and instrumentation lab. Okay, now. So what is the multiplexer? Simple cases, multiplexer is nothing but which many to one. Simple way is a many to one. Many inputs, only one output. But choosing one input out of many is going to be done by the selection lines. Choosing one input out of many is going to be done by the selection lines. As all of you know that one, but let me review this. Let me give this one. I think the paper is not good, but let me take the diagram. I'm assuming that having the 4 inputs, only one. It is called as a 4x1 multiplexer. So I'm going to use the 2 selection lines, S1, S0, I0, I1. I think you are recollecting the information which we've seen in our lab. Okay, this is the output signal. So it is a many to one multiplexer. Many to one multiplexer means many inputs are there, only one output is there. Same concept we are going to use over here. Same concept we are going to use over here. Okay. So in this case, there are 2 types of multiplexers. Means depending on the channels, input information, whether the information in terms of the analog or whether the information in terms of the digital. There are 2 types of multiplexers. One is a digital to analog multiplexer. Another one is a analog to digital multiplexer. One is a digital to analog multiplexer. Another one is a analog to digital multiplexer. Means if the many inputs, multiplexer is nothing but many inputs and one output. If the many inputs which are coming from the different channels, different sources, they are in the digital format, and I'm assuming that the communication path is going to be the analog signal, then I'm going to use the digital to analog multiplexer. Digital to analog multiplexer. There are 2 different ways to construct the digital to analog multiplexer. One is using the SIMA. I'm assuming that there are 4 channels which are trying to send the information through the analog communication path. So here what I'm going to do is I'm going to use 4 different DA converters for each and every channel which are sending the information in terms of the digital format. Means I'm having the 4 channels. Those 4 channels are sending the information in terms of the digital, and that particular information should be transferred through the analog communication path. At that time, what I'm going to do is, as I said, there are 2 different ways to construct the digital to analog multiplexer. One is using the separate DA converter for each and every channel, and another one is using only one single DA converter, to send to form the digital to analog multiplexer. So here, as I said, in order to perform the multiplexer, we are supposed to choose one out of many. That is going to be done by the selection lines. Similar to this selection line process, here we are having the gating and control unit. So this particular gating and control unit, what it is doing is, it is taking the responsibility to choose one channel out of many. Only that particular channel DA converter is going to be enabled, and that particular DA converter is enabled, and that DA converter converts the digital information into the analog format, and that analog information is passing through the analog communication path. So that is the this is the one way of constructing the digital to analog multiplexer. What is the case here? When we are having the many channels, all the channels are sending the information in terms of the digital, and we are converting that one into the analog format using the digital to analog multiplexer. Okay, so there are 2 ways to construct the digital to analog multiplexer. One is using the separate DA converter for each and every channel. So another one is using only one DA converter. So what is the disadvantage of this one? When you are using the separate DA converter for each and every channel, then the number of digital to analog converters which are used in our system, in our multiplexer, is going to be increases. Then obviously the complexity of the circuit is going to be increases. Obviously the cost of the circuit is going to be increases. If the components are increasing, obviously the cost of the circuit is going to be increases. So to avoid this one, what we are going to do is, we are going to opt the another method. Instead of using the separate DA converter, I'm going to use only one DA converter for all the channels, and they are given as an input. They are giving the digital input to this particular DTA converter, and this particular output of the DTA converter is means the digital information is converted into the analog. Now this analog information is going to be stored inside the sample and hold circuit. Sample and hold circuit means I'm going to have the separate sample and hold circuit blocks for each and every channel. Again, selecting the channel out of many is going to be done by the gating and control circuit. Here, instead of using the multiple DTA converters, we are using only one DTA converter, and this DTA converter is converting the digital information into the analog format, and the information is available in the analog format, and this information is going to be communicated through the communication path using the this particular setup. So here, why I am using the sample and hold circuit means sometimes means we are not sure that all the, if we are sure that only one channel is going to be acquires the analog channel, then we no need to go for a sample and hold circuit. If at all the signals are trying to pass through the analog communication path, it is very difficult to use only one path for multiple channels. At that time, what we are going to do is we are going to use the time slicing format. If we are having the T time period, this particular T time period is divided into 4 blocks, 4 time slots. So one time slot for one channel, another time slot for another channel, another time slot for another channel, and so on. Okay, so like that we are assigning the time slot for each and every channel. Okay, so at that time when we are assigning the time slot for this channel, if this channel is having the information, we may lose the data. So to avoid that one, we are using the sample and hold circuit to hold the information when this channel is under process. And when this channel is under process, to hold this information, we are using the sample and hold circuit. And just like these two, the remaining is also same. So that means it is a reduced diagram to the previous digital to analog multiplexer diagram. And another case is when you are having the channels information in terms of the analog. Means we are having the multiple resources and they are trying to send the information in terms of the analog, but the communication part is in the digital format. Then what we are supposed to do? We are supposed to convert. We are supposed to use the analog to digital multiplexer. There are different ways again to design the analog to digital multiplexer. One is what I am going to do is I am going to use the analog inputs. I am using the relays to communicate. So here these 4 channels are there now. Choosing one channel out of many is going to be done by this particular block. And here, as we are using the as we are using the digital communication path, I am using the analog to digital converter. So analog information is converted into the digital format. Again, just like the previous case, if all the channels are trying to send the information at a time, it is not possible. Again, the allotted time slot is going to be divided into equal parts, which we have seen in the classroom during the 3rd semester. So when you are having the 4 devices, would like to access a time period, 1 minute time period, then each device is going to be gets the 15 seconds duration. So like that, the information is going to be transferred. So one of the best example is whatever the information means in the city buses, we are using the matrix displays. It means some bus number, route number. Let us suppose I am using the 218D, which is a Dilshugnagar bus. So when we are using the 218D and it is printing on the display and keep on moving, at that time all of us think that the LEDs are glowing and it's moving. Actually, all the LEDs are not glowing at a time. We can't see that one. Actually, only one row of LED is going to be blink at a time, but that duration is only for a microseconds range, certain period of microseconds range. So that we can't observe with our naked eye. So because of that, what will happen? We think that all the LEDs are glowing at a time, but it is not like that. Only one row of LEDs are glowing at a time, and that row means from one row to another row, another row. It is a keep on continuously moving, what is sending the information, and it is changing within the microseconds range. Means the LED glow and off is going to be done within a microseconds range. Because of that, we can't differentiate that only one row is glowing. Okay, it is just because of our naked eye problem. Naked eye can't observe that variation within the microseconds range. Okay, so just like that. Here also, when the multiple signals would like to send the information, don't think that multiple signals are sending the information at a time. Even though they are trying to send the information at a time, there is a time slot. What I mean to say that if we are having the 1 minute of time period allocated for all the channels, then that time period is equally divided into the number of channels. So let us suppose if I am having the 4 channels, then 1 minute duration. So 1 minute duration is divided into equal format, means 1 minute is a 60 seconds, then 15 seconds for each and every channel. So after 60 minutes completion, the first channel is going to be guessed the next 15 seconds, means 15 seconds for each and every channel. It is called as a time slicing. Time slicing. Even though the multiple channels are appearing at your TV tuner, don't think that all the channels are available at a time. Only there is a time slot allocated for each and every channel, which we can't observe with our naked eye. That is the main that is the main advantage of having the multiple channels. Means when we are having the multiple channels, even though there is a time slice, we can't observe that one, because that time slice is varying very fastly in nanoseconds range and microseconds range. Because of that, we can't observe that variation. Okay, now, so here also same thing. When the multiple sources would like to send the information at a time, what we are going to do is only one analog to digital converter is there, that is not going to be processed all the channels at a time. So because of that, what we are going to do is we are going to again use the sample and hold circuit for different channels, and they are sampling the information, holding the information for some period of time. After, whenever there is a time slot allocated for so and so channel, that information is going to be processed by the analog to digital converter. This converts the analog information into the digital, sends the information. Again, the next channel will get its turn. Okay, next channel will get its turn, and it is going to be processed by the analog to digital converter. If you are getting confused with this one, let me show you a simple plot. So 0 to t, this time period is equally divided into 4, t1, t2, t3, t4. t1 time period for channel 1, t2 for channel 2, channel 3, channel 4. After finishing this time period, the t1 the channel 1 is going to be gets its next turn after this time period, means t1 plus t. So means whatever the duration you are taking, if I am assuming this entire duration is a delta t, then t1 plus delta t, t2 plus delta t2 or delta t, t3 plus delta t. Like that, it is going to be get the next time slot. Means the entire time period is divided into equal format, equal slices. Each channel is getting one time slice, one time slice, one time slice, one time slice. So this is what we are having over here. So when the multiple channels are trying to send the information, we are going to use the sample and hold circuit. Because of that, we are able to hold the information in order to avoid losing of the data, and that information is going to be processed by the analog to digital converter. So this is about analog to digital multiplexer. And one more method is, instead of using the previous case, what we are going to do is we are going to use the counter type analog to digital multiplexer. So here, in this case, I am using the comparator. So you know that the main intention of the comparator is quantizing the value. In communication terminology, if you say the comparator is nothing but the quantizing the value. When we are going to quantize the value, means when you are trying to convert the analog information into the digital format, we are supposed to quantize the value. It looks like different, but it is the actual scenario. So when you would like to convert the analog information into the digital format in communication path, analog signal is nothing but what? First define the analog signal. Analog signal is nothing but what? It is a continuous signal. It is a continuous signal with respect to the time. So whose amplitude is varying with respect to the time, it is an analog signal. Analog signal. Digital signal is nothing but, as per the definition, digital signal is nothing but a signal whose amplitude is quantized with respect to the y-axis. A signal whose amplitude is quantized with respect to the y-axis is called as a digital signal. But if you want to convert the analog information into the digital format, first of all, the analog information is converted into the discrete, which we have seen in the classroom. But again, I am repeating this one to recollect the information. So this information is converted into the discrete format with the help of a switch. So this switch is going to be open and closed with a certain period of time. So we used to call that one as a 1/2t. So I'm not considering this entire concept. So this one is called as the sampling theorem. So twice the input signal frequency, there is a certain rule, but I'm not considering this one. So we are using the switch. This switch is going to be convert the continuous signal into the discrete format. Continuous signal into the discrete format means time slices. After a certain time period of time, we are going to get this amplitude means this amplitude, this amplitude, this amplitude, this amplitude, this amplitude, this amplitude, and so on. Okay. So this is a discrete signal. Now, in order to convert the discrete signal into the digital format, I am going to use the comparator. Okay. So comparator, I am assuming that the negative terminal is connected to the discrete signal. Negative terminal of the comparator is accepting the discrete information, and positive terminal is connected to the reference signal. I am taking the condition in such a way that if this signal is less than the reference level, then the output is going to be the positive. Means I am going to get the positive pulse. If this negative discrete signal, if the negative terminal is greater than the reference signal, I am going to get the negative pulse. So means if I am taking the 5 volts less than if this voltage is less than the 5 volts, then the output is going to be the positive. If this voltage is greater than the 5 volts, means if it is the 6 volts, obviously we are going to get the 5 minus 6 now. 5 minus 6 means 6 is greater than the 5 now, so output is going to be the negative. Means that we are going to get the negative pulse and positive pulse. Negative pulse means digital signal, discrete signal is converted into the digital format. And if you see this one, this amplitude is fixed on the y-axis. So that's why digital signal is nothing but the it is a quantized. A signal whose amplitude is quantized on the y-axis is called as a digital signal. Okay, it's called as a digital signal. Analog to discrete, discrete to digital with the help of the comparator. So based on this concept, we are having right over here. Here, the comparator is always comparing the reference signal with the present analog inputs are comparing with the reference signal. So this reference signal is coming from the digital to analog converter. Whenever this reference signal is less than this analog input, then we are not going to get the output. If the reference signal is greater than the analog inputs, then obviously the counter is going to be transfers the information in terms of the digital. Means output is going to be available in terms of the digital. So analog is converted into the digital format. Means analog is analog. This one is an example for analog to digital multiplexing operation. We are multiplexing the individual comparator signals and we are displaying that one as an output in terms of the digital. Okay, now, so this is what we are having in analog to digital multiplexer. Okay, now, so with this, I think analog to digital multiplexers are over. Okay, so we have seen the data acquisition system. We have seen the analog to digital multiplexer, digital to analog multiplexers, and the next concept is the last concept is our IEEE 488 bus. IEEE 488 bus. IEEE 488 bus. So which is there in your textbook, which I sent you. I'm going to send this information to you people in the group. Okay. So this is the information. Here IEEE 488 is nothing but it is a Institute of IEEE stands Institute of Electrical and Electronics Engineers, and the standard number is the 488. So this is a one kind of bus protocol used for communicating the devices, that to the digital communication. In order to establish the digital communication among the devices, we are using this particular bus. Okay, now. So this bus is meant for short distances, not for the long distances. Approximately 20 meters length. Approximately 20 meters length. And this bus is able to send the information in terms of the TTL logic family. They are using the TTL logic family. Okay, now. So TTL logic family is nothing but transistor logic family. So when we are using the transistor logic family, we have some thumb rules. Thumb rules are nothing but when you are taking one IC now, that IC is expecting the information at the input lines in one format, and the IC is giving the information at the output lines in another format. Expecting the information in one format and sending the information in the another format. When the information is coming into the IC, means if you are taking the TTL family, all of you know this one, we have seen that one also. TTL family, the binary 0. If you want to send the information to the IC, which is following the TTL family rule, the binary 0 is going to be treated as a 0 by that particular IC if that particular voltage is varying from 0 to 0.8 volts. 0 to 0.8 volts range. So the TTL family is supporting the TTL standard. So TTL family means I am going to take the voltage range. This is for the input, this is for the output. So 0 to 0.8 volts is treated as a binary 0 for the input case. 2.0 to 5.0 volts is treated as a binary 1 for the input case. When the same TTL family IC is trying to send the information, then at the output of this that particular IC terminal, the output, if the output is varying from 0 to 0.4 volts, it is going to be treated as a binary 0, and if the output is varying from 2.4 volts 5 volts, it is going to be treated as a binary 1 in case of the output scenario. In case of the input scenario, 0 to 0.8 volts is a binary 0, 2.0 to 5 volts is a binary 1. In case of the output scenario, 0.04 to 0.4 volts is a binary 0, 2.4 to 5 volts is a binary 1. So this is the TTL family logic. See, this rule is going to be used by the IEEE 488 bus. Why I am saying this one means, we have seen one standard, RS232 standard, the protocol. So when we are taking the RS232, as we know that we have seen in the microcontroller case, RS232 standards are nothing but binary 0 is nothing but if the voltage is varying from -3 volts to -25 volts, it is treated as a binary 0 by the RS232 cable. And if we are using the +3 to if we are using the binary 0 is nothing but the +3 volts to +25 volts. If we are means if the voltage, if we are so RS232, when we are taking the RS232 cable, that RS232 is converting the binary 0 information into the +3 volts to +25 volts range, and the binary 1 information into the -3 volts to -25 volts range. -3 volts to -25 volts range for the binary 1, +3 volts to +25 volts range for the binary 0 in the RS232 case. Just like that, here also, when we are using the IEEE 488 bus for communication, then this particular IC is following this particular cable, the communication path, the bus is using the TTL family logic. Now, using this particular bus, there are the female connectors as well as the male connectors. We know the female as well as the male connectors. Using this particular bus, we can interface a maximum of 15 devices. If you are going to the practical scenario, we can interface the 15 devices, and those devices, when we are interfacing the multiple devices, as we know that we are supposed to have the common grounds among the devices. If we are not having the common grounds among the devices, then obviously we can't send the information from one device to another device. But the problem is, when we are trying to communicate different devices with the common ground, there is a voltage difference between the one ground of the one device to another ground of the another device. So that voltage change, that voltage difference is going to be introduced into the bus as a noise. So what we are supposed to do, in order to avoid that one, what we are going to do is, we are supposed to use the Schmitt trigger device along with the diodes. Schmitt triggers along with the diodes. With the help of the Schmitt trigger along with the diodes, whatever the ground differences which are there among the devices, means if I am taking one device, that device, I am assuming that the ground of that device is a 0 volts. Another device, the ground may be the 0.003 volts. Another device may be the 0.01 volt. Means there is we treat that one as a ground, but when you are comparing all the grounds, then obviously there is a difference. So that difference is going to be trying to entered into the system in terms of what? In terms of